My today's topic is topicity or topic relationship. Now this topicity explains the relationship between homomorphic ligands or phases with rest of the molecule. Now the question is, this new term homomorphic means what? Homomorphic means identical, means in this topic we are going to discuss the relationship between the identical ligands or identical phases. Now let us go to the classification, means what are the terminologies which are going to use in this topic. Homomorphic ligands or the homomorphic phases can be of two types. One is homotopic, another one is heterotopic. Now the heterotopic ligands or the heterotopic phases can also be subclassified into two headings. One is stereoheterotopic, another one is constitutionally heterotopic. And stereoheterotopic ligands and phases can also be subdivided into two categories. One is the enantiotopic and another one is the diastereotopic. Now the question is, in order to understand this relationship under the heading of topicity, how to proceed? Now how to find out the topic relationship? Now there are two methods are there. One is the addition substitution method, which is easy to apply and less chance is there to do mistake, and another method is also there, that is known as the symmetry method. Now let us learn how to apply addition substitution method in order to get the relationship between homomorphic ligands and the phases. Now in this method there are two terms combined together, one is addition, another one is the substitution. So when we will try to find out the topic relationship between homomorphic ligands, in that case we have to apply substitution, and when we will try to find out the topic relationship between homomorphic phases, in that case we have to apply addition method. Now first let us consider the substitution which we are going to apply to find out topic relationship between the ligands. Now first we have to consider the homomorphic ligands. Homomorphic ligands means they are the identical atoms or they can be identical groups also, like two hydrogens or two OHs or nitros or chlorines or two nitrogens or two NH2s, like that. They can be atom or they can be groups. But if they are not homomorphic, means we cannot be able to establish the topic relationship between hydrogen and oxygen. We cannot be able to establish the topic relationship between CH3 and nitro. We cannot be able to establish the topic relationship between chlorine and the bromine, as they are not homomorphic or identical. Now let us first go for the substitution method, means among which we have to find out the topic relationship. First we have to replace those groups or those atoms one after another by using the some other ligands or the some other groups, or if possible the higher isotope, one after another. And after substituting, then we have to investigate. After substitution, if we get homomers, then the ligands are homotopic. After substitution, if we get the structural isomers, then ligands are constitutionally heterotopic. After substitution, if they are stereoisomers, then they are stereoheterotopic. And as we have already discussed, stereoheterotopic ligands or phases can be of two types. Here after substitution, if we get enantiomers, then those ligands are enantiotopic. And finally, if after substitution, if those ligands After substitution, if we get the diastereomers, then those ligands will be considered as the diastereotopic ligands. Now let us consider ethyl alcohol, and at first step we are trying to find out the topic relationship among the 3 hydrogens of CH3 of ethyl alcohol. Now as we have learned in the previous case that all the 3 hydrogens of methyl group, one after another, they should be replaced by another ligand. In this case we are replacing these hydrogens which are labeled as H1, H2, H3. Those one after another we are replacing them by heavier isotope deuterium. And after replacing, what we are getting, the 3 molecules, we have labeled them as X, Y and Z. Now by who are they, X, Y and Z? If they are homomers, then those 3 hydrogens will be homotopic. If they are constitutional isomer, then these 3 hydrogens will be constitutionally heterotopic, if like that. So now after investigating X, Y and Z, we have come to know they are exactly similar because they belong to the molecular formula DCH2CH2OH. So therefore the 3 hydrogens of methyl group of ethyl alcohol, they are homotopic. Now coming to what it is called the CH2 of the same molecule, means then my next question is we will try to find out topicity between the 2 hydrogens of CH2 group of ethyl alcohol. Now before establishing this, I would like to mention one thing, that if a given molecule is achiral and the topic relationship, what we have to find out, if atoms or ligands are attached with one carbon of type CABXX type, where A and B are the non-identical groups and the X is the identical atom on which we have to find out the topic relationship, then topic relationship between the 2 X will come out as enantiotopic. Means in this question where we are trying to find out the topic relationship between the 2 hydrogens of CH2 of ethyl alcohol, if we solve by substitution method, then also we will get that 2 hydrogens are enantiotopic. Now in case of ethyl alcohol, if we try to apply that substitution method, another if we replace it by D, then the resultant 2 molecules will be having chiral centers and one will be R enantiomer, another one is the S enantiomer. So therefore after replacement what we are getting, those are enantiomers. So definitely the 2 hydrogens of CH2 will be enantiotopic. Now let us apply this concept to the another molecule glycine, where also the question is the identify topic relationship between the 2 hydrogens of CH2 of glycine, and if we check, the glycine is one achiral molecule and the 2 hydrogens are attached with the carbon, that carbon is CABXX type. So the 2 topic relationship between these 2 hydrogens will be enantiotopic, and we can confirm this answer by applying the substitution method, where 2 hydrogens one after another, if we replace it by D, then we will be getting 2 molecules. Those 2 molecules are enantiomers, one is R, another one is the S. So in that way also we can be able to confirm the 2 hydrogens of CH2 of glycine are enantiotopic. Now we will switch over to the next molecule, where these enantiotopic ligands may not be present in the one carbon, means in certain cases where the homomorphic ligands are present in the 2 different carbons, then CABXX type pattern we will not be able to apply, and we have to apply only the substitution method. In order to show this, we are taking one example of mesotartaric acid. Now the question to be answered is the identify the topic relationship between the two OHs of mesotartaric acid. Now if we replace these two OHs one after another by OD, then whatever we are getting after replacement, those are labeled as X and Y. Now X and Y are the mirror images, so therefore X and Y are the enantiomers. So if X and Y are enantiomers, therefore the two OHs which are present in the mesotartaric acid are enantiotopic. Now let us switch over to the diastereotopic ligands. Now diastereotopic ligands can be present in the chiral molecule, as well as diastereotopic ligands can also be present in the achiral molecules with some double bonds or something like that. So let us first discuss the diastereotopic ligands which are present in the chiral molecules. Now if any chiral molecule contains CABXX type center, then the 2X will be diastereotopic. Now let us apply our concept in case of one chiral molecule. Say the question is identify the topic relationship between the two hydrogens of benzyl group which is present in the phenylalanine. Now phenylalanine is one chiral amino acid where first of all it is chiral, and second the two hydrogens are present in one carbon of pattern CABXX type, where A and the B are that A is the chiral center and the B is the phenyl, means these two are the non-identical groups and the X is the hydrogen. So definitely the two hydrogens will be diastereotopic. Now by using the substitution method also, if we after substituting two hydrogens by deuterium, we will get the two compounds. Those two compounds will be diastereomers. So if they are diastereomers, as because they are diastereomers after substitution, therefore the topic relationship between the two hydrogens of a benzyl group in phenylalanine, they are diastereotopic. Now let us discuss the diastereotopic ligands which can be present in the achiral molecule. So for that purpose we are taking some molecules which will be having the double bond, and they will be having some specific pattern as it is written clearly within the square box. Now the 2X will be here also the pattern will be ABXX type, but the AB will be present in one side of the double bond and the XX will be present in the another side of the double bond. Now the topic relationship between these two X will be they are diastereotopic, and as a whole the molecule is the achiral molecule. Now the same relationship can also be established by replacing our old substitution method. If the two X are replaced by the D, then we will be getting the two compounds. Those are diastereomers, either they are cis trans, otherwise they are E and Z. So therefore the 2X will be diastereotopic. Now coming to the last part of this, means one more topic relationship can also be established, that is the constitutionally heterotopic. Now in order to prove that, I have taken the molecule 2,2-dichloroacetic acid, and the question is try to find out the topic relationship between the two hydrogens of this molecule which are labeled as the HA and the HB. Now it is very clear that HA is attached with the carbon and the HB is attached with the oxygen. So therefore they will be constitutionally heterotopic, and the same thing can also be proved by replacing HA and HB by deuterium. After replacement we will be getting some constitutional isomers. So therefore HA and the HB of 2,2-dichloroacetic acid will be constitutionally heterotopic. Now coming to the topic relationship establishment between the two phases of the molecules, in that case we have to apply the addition criteria. Means mainly this topic relationship will be established either between the two phases of alkene, otherwise between the two faces of the C double bond O. Now in both the cases we have to apply addition criteria with some understanding, means when we have to apply the topic relationship for the alkene, then only epoxidation only we have to apply among all the additions, other additions are not allowed. And in case of the carbonyls, any addition we can apply in order to understand the topic relationship between the two phases. Now after successfully applying epoxidation in case of the two phases of alkene or any addition in case of the carbonyls, after that whatever we will be getting the two products, those two products, if they are homomers, then the two phases will be homotopic. If these two products are enantiomers, then the two phases will be enantiotopic. If those two products after addition they are diastereomers, then the two phases will be diastereotopic. Now I have given the 5 examples of the homotopic phases, and in due course we will prove by in case of the alkene we will apply the epoxidation, in case of the ketones or aldehydes we will apply the any other addition in order to find out topic relationship between the two phases. Now we have taken a molecule cis-2-butene and we are applying the epoxidation. Now the epoxidation, it's a planar molecule, so the epoxidation can happen on the top, otherwise epoxidation can happen at the down. So in this way we have to write the two molecules, and after writing it is very clear this molecule has one sigma plane. So therefore whether oxygen is coming and on the top or oxygen is coming at the bottom, these two molecules are homomers because they have the sigma plane, and if they are homomers then the topic relationship between the two phases of cis-2-butene are homotopic. Now we have taken one more example where we have to find out the topic relationship between the two phases of C double bond O which is present in benzophenone. Now in this case epoxidation not possible, we are going for the Grignard addition, methyl magnesium iodide followed by hydrolysis, so that it will be converted into the tertiary alcohol. Now this tertiary alcohol is one achiral molecule because there are two phenyl groups are there. So therefore whether the methyl is coming from the top or the methyl is coming from the down doesn't make any difference, and therefore the topic relationship between the two phases of benzophenone are homotopic. Now let us apply this concept in order to find out the topic relationship between the two phases of propene. That propene is having the double bond and we are trying to find out topic relationship for the C double bond sheath. So therefore answer should come based on epoxidation and no other addition is allowed. So the same way oxygen can come from the top, oxygen can come from the bottom, and after writing these two structures, if we investigate these two structures, then it is clear that after epoxidation we are getting one chiral center, and one chiral center is S, another chiral center is R. So therefore these two epoxides are enantiomers. So as because we are getting two enantiomers of epoxides, therefore the two phases of propene are enantiotopic. Now coming to the second molecule, that is identify the topic relationship between the two phases of trans-2-butene in a exactly similar way. This is C double bond C, so therefore we have to do the epoxidation. After doing the epoxidation, the epoxides if we investigate, we are getting two chiral centers, and if we do RS of these two chiral centers, one epoxide it is coming SS and the another epoxide it is coming RR. So these two are SS and RR, so therefore they are again enantiomers, and hence the two phases of trans-2-butene are enantiotopic. Now coming to the apply the same concept towards the carbonyl compounds. So we have taken the two molecules, one is acetaldehyde and another one is the acetophenone. In this case we can add any reagent provided those are not present in the double bond. So because of that acetaldehyde is subjected to the reaction with the ethyl magnesium iodide followed by hydrolysis, because ethyl group is not there in this double bond, And acetophenone is also allowed to react with the ethyl magnesium iodide followed by hydrolysis. After this, from acetaldehyde we are getting the 2 enantiomers, from acetophenone also we are getting 2 enantiomers. Therefore, the 2 phases of acetaldehyde and the 2 phases of acetophenone are enantiotopic. Now let us apply this concept to the diastereotopic phases, and in this case the given molecule we have to identify the topic relationship between the 2 faces of the C double bond O which is present next to the chiral center. Now this chiral center, as because the chiral center is there, and when we will apply the addition criteria to the C double bond O, then definitely we will be getting the one new center. So as a whole you will be having, the molecule will be having the 2 chiral center. Out of them one is present in the substrate, another because of this addition we are generating. So the old center is constant, new center will come in a 2 different possible way. So as because definitely we will be getting the 2 diastereomers after this addition criteria, which will be applied to the C double bond O which is next to the chiral center. Now as because after addition we are getting the diastereomers, therefore the topic relationship between the 2 C double bond O will be diastereotopic. Now let us apply our concept whatever we have learned in this lesson, that we have to identify the topic relationship between the circled hydrogens, and the circled hydrogens are present in the 2 different molecules. So in the left hand side which compound is there, that is a trans compound, and the that molecule is a chiral compound, and the 2 hydrogens are present in a carbon of pattern CABXX type. So as a whole the molecule is chiral and the CABXX type is present in the chiral molecule. So the topic relationship between these 2 hydrogens will be diastereotopic. But the compound in the right hand side, that is a cis compound, and it's a achiral compound. The sigma plane is present at the passing through the center of the molecule, dividing the molecule into the 2 equal halves. So as because as a whole the molecule is achiral and the 2 hydrogens are present in the carbon of pattern CABXX type. So therefore the topic relationship between these 2 hydrogens will be enantiotopic.